All right, good morning. Very, very good morning, everybody. We have gathered here to discuss value-oriented design by example. And I would like to know more about you. I know we are all at our homes and in remote locations. We are not in the same room, like Mahindra also said. But I would like to hear from you on about a few things. So please bring up your chat, and could you please type in your chat the answer to this question? And I would love to see what the results look like. No. Yeah, Nikhil, I know. Okay. It's going as yes, almost everybody. Okay. No. So in all the attendees, we have so far got 2 no's and mostly yes. So OO seems to be the dominant programming style. Bjarne Strostrup had also said that, in the 90s, when object-oriented had not caught on and all these conferences had started, by the end of the 90s, it was seen that it was really, it had become the dominant way of programming. And so he said that he had won. Their objective was met. Okay, next question, guys. Have you implemented using functional style programming? I know dominantly it is object-oriented, but any wandering around this zone, functional programming style? Yes, Nikhil. Ooh. 2, 3 yeses and a few no's. Okay. The usual suspects. I now know by name who's not doing O and doing FP. Cool. I look forward to your thoughts in this session also. Okay, thank you very much for your responses. And last one, what according to you, now this is a little textual, are qualities of good code? Yes, I see easy to understand, maintainable, readable, brevity, maintainability, extensibility, no tight coupling, well tested, scalable, modularity. Testability, readability, simplicity, unit tests should be present. Makes sense. Readability. Right. If this was a word cloud, I think I could have planned that, but I think this interaction is much better. So I see readability, modularity, maintainability, and also testing has been specifically mentioned. And scalable is also one of the points, which is great to see. Let's see, really, if we have covered all of these. I usually talk in terms of effective, efficient, and elegant. Your prime concern should be doing it correct, effective. Then you should be high performance, efficient, and then elegant. And I don't know, I think I put it as a then, but I cannot really, the first two are very important in our world. Elegant is also should be important because we might not prioritize ourselves over other things, but that's not the right way to go about things. This is from Tony Van Erd's presentation. This excerpt talks about some other things, which is unsurprising, intuitive, solid is mentioned, reusable, replaceable, and concise. I think there was a hint of that in your answers. Changeable, easy to use, and in the pit of success. Correct, proven, tested, works, fast, efficient, beautiful, rare. Wow. Non-existent, rumored to exist. Okay, so this was, I think I would agree with all of these points. And all I would say is it should be easy to use correctly and difficult to use incorrectly. You should fall in the pit of success. And with that, I just wanted to tell you what it means. But here, first, we look at what Bjarne Stroustrup thinks is clean code. This was asked by Robert C. Martin, Uncle Bob, to him, and that was his answer. I would just highlight these aspects. It should be hard for bugs to hide. This is a very desirable quality, and none other than Dr. Stroustrup can say this. And also very important, so as not to tempt the people to make the code messy. You don't want to make the mistake which you didn't even try. I mean, sorry, the definition of mistake is that, but you don't want the code to go down south, because what I think is we should fall in the pit of success. It should not be an uphill climb where you are actually struggling to push the ball uphill and against gravity, and using up all your force but not getting anywhere. Rather, it should be in the pit of success, where anywhere that you go around, you would come back to the center point. Okay, but I would always, I've said this always, that code always spirals. Whether it spirals up towards better code or down, it always accumulates more code like it. So code always spirals, according to me. And going with the theme of the of CppIndiaCon 3 2023, I had to put this spiral galaxy. So code always sucks in one direction, and it is up to you to make sure that it doesn't go in the direction that you don't want. And things go bad over time. Things would not be as good as when you started. We often say this about our code, and with time it deteriorates. And finally, you come to a stage that it has to be rewritten. This is one of the worst things to do. I guess we could do a lot more software engineering before this, and we should not reach this stage. If finally rewriting is what you have to do, it's sorrow. But it happens. And every time you start fresh, like here we have this really funny one. Every time you start fresh, you're all determined, and you start with a very clean slate, and with all good intent and a good design as well, and good thoughts and good principles, good goals and guidelines. But then over time, it accumulates things that you don't want. It shapes the way you don't want it to shape. We should not let that happen. And I guess you should keep on maintaining your code all throughout with every little change. But this would be a whole different talk. This is not what we are talking about today. Programs are meant to be read by humans and only incidentally for computers to execute. This, I'll remind you, is from Donald Knuth. He's Donald Knuth, whose quote you saw yesterday in Mike Shah's session about premature optimization. So I'm reminding you, I'm staying with the celebrity of the season. But such an important thing. It is very important to be able to understand and enhance the code. Otherwise, your ability to go at speed to the market and surviving and sustaining will be at risk. Okay, so let's look at some object approach, well-known object approach. What is it? Object approach is about modeling the real world. Okay, you have in code what you see, similar to things that you see out out and about. Okay, it's things like cars, or you model these kind of things. Okay, and various objects, and create objects out of those classes. All right, so let's look at the objects world. So of course they are real world objects, but we also come up with some helping entities like the helper, the manager, the processor. These kind of suffixes, when we use, we are building up something imaginary in this world. Okay, in this world of so-called realistic objects. The identity of these objects is very important. It is where they are placed, how they are known, their address, their reference is very important because it's a very reference-based world. Inheritance takes its course, and it's a perfect mechanism where it works. It works like a charm, like you have GUIs, which is the best place that object-oriented can be used. But we have other places where I'm just showing this talk from 5-minute talk from John Kalb. I would ask you to go back and see why do the cool kids not like OOP. And the point he's making here, I'm just putting a few seconds of his talk here, is that we don't know what the actual type is when we write generic code or common code. The compiler doesn't know when we write that code. In case of object-oriented. In object-oriented, even while executing, the compiler does not know what kind of an object is being passed. It has to go through indirections and make things happen. Whereas if you use the templates, it is known to the compiler exactly what type you're talking about. It can inline, it can eliminate things and reason about things and make some optimizations. But this was an aside anyway. So back to our point. Objects tend to be non-copyable, and they have a reference-based use. They worry about lifetime and changes, and their state changes, and there is sharing between the objects. Relationships and polymorphism come in the picture, and it's about things which with associations and contains. Various kinds of relationships that we see in code. And this is Sean Parent talking about one such relationship where there is a dependency on something called as a shared pointer. You have this, Sean says, he reasons that this is just like a global because so many people are sharing, it's just like a global, and it is everybody is trying to use the same kind of a thing. Okay. And this is the kind of thing that may cause spooky action at a distance, which means a side effect which you do not intend to make, but you happen to actually do. All right. And Tony Vanner, in his this superb talk, says that state leads to objects, objects lead to references, references lead to sharing, sharing leads to entanglement, and entanglement leads to suffering. It's apt, and I'm sure you all agree with this, that the state sharing entanglement is what causes so many things which you don't intend, what we fondly call as bugs. Now we switch to looking at values. Values are just like int. Okay, and they are defined to be something like regular or at least semi-regular by Alex Stepanov. Okay, they are, if you see the definition of what is a regular, they are copyable, default initializable, and equality comparable. Okay, so all the regular math kind of things are applicable. For example, if you make a copy of X, it has to be the same as equal to X. If you assign X to Y, make their values same, then they ought to compare the same, irrespective of which values on the left hand side. These things are ephemeral. For example, you cannot touch or feel. It doesn't come into existence. What I'm talking about is a string. Let's say a string with CppIndiaCon. It doesn't come into existence and come and go and end its lifetime. That kind of a value is always there. Okay, a number 22, it's always there. Okay, and we in our data types, ints and uints and uint64s, we are able to represent a certain range of these numbers, and we try to stay within that. But these numbers always existed; they will always exist, whether we exist or not. And to be regular and to create values, we need to do a few things. Of course, as we saw, we need to be have a default constructor. We need to be able to copy and move construct. We need to be able to copy and move assign, and we need to be equality comparable. So if you have entities, things in your system which can do this, they are value like, just like int. But all these are generated by the compiler, right? I can hear some of you say. All of these can be generated by the compiler. So do you write yours yourself by hand, or do you let the compiler write these for you? And that's also something that we have to look at. Today, we'll also look at a bit of rule of zero. But I'm just reminding you, the rule of zero allows the compiler to write it for you, and you better let it do its job. Okay, value types use trivial types. They can be structs. They in turn have trivial types within them. And once you have, let's say, a struct with 3-4 ints, let's say a point with 2 ints, x and y, this point itself is also a value type because it is made up of, in turn, just value types. You can construct, let's say, a set of points, a diagram, let's say, a figure, an image, a line, which is a set of points, because that also transitively gets the property that if it only contains points, it is also a value type. It can also copy, move, and do all those things. If all members can independently change, that is, you use a struct, okay? But you should create a class in case you want to manage how they change. For example, here we are seeing a class on screen, and the class defines some of these things and has private members. If you care that x and y should not change independently, which somebody could, then you got to use a class and make it private, or use a struct and make it private, basically. But if you don't care, like points in space can move in any direction. If anybody updates x only, it's okay. It has laterally, it has made a linear movement in that direction. That's fine too. Then you could just stay with struct, and with struct you just get all of those. There are no private members, and so you get all the benefits of rule of zero. Okay, and values are immutable. Thank you, Ayush, for pointing it out. Values are immutable. That's how the functional programming actually recommends, although we are in C++. So, but I don't want to relax the definition side of it. Okay. And associated with these value types are pure functions. Pure functions are those functions which just depend on the types provided. So if you have a function called as inflate and you are giving a tire to it, okay, a tire T, do you think everything is okay with this? Is there a problem? Everything is okay, somebody says. I guess copy, yeah, copy, yeah. So somebody says copy is a problem. I think normal air or nitrogen, good one. So what is not available here to inflate is the value. When you go with your vehicle to the place where you can fill air or nitrogen, you have to tell them how much you want to fill. So here it is acting on its own accord, and this is hidden information. Either it is working on some global, or it has some hard code value inside, which if you give a cycle tire, it'll just burst it. So it's dangerous, and this kind of things is what makes this function not pure. And so how much to inflate is the question which is not answered by the user. And now if you make it this way and you have to pass the pressure, then this functionality can do its job, and just its job. The quality of a pure function is that it will give you the same value given the same inputs at any time in the universe. Okay, so it's a fact, mathematical. There we go. Okay, so values, functions, and pure operations. These are the qualities that we have discussed, and I've added composition there because, like we discussed, if you add things which are regular into another data type, that data type also becomes a pure one. I'm sorry, a value object. Now let's put both of these things side by side, and let's see how they compare and contrast. So here we have values in string. We don't care what where they are placed, but the value is important, and they can come and go in your program, but the value means one and only one thing. But the identity is on the right hand side for objects is very dear to the object. If you speak to somebody called as Mahendra, it is only Mahendra that you are speaking to. If you are holding the cricket ball from the final match in the 50th over, that is the only ball that you're talking about. So it has a very specific instance related to it. It can have state on the right hand side, whereas if they are immutable, timeless, ephemeral, and regular on the left hand side. Okay, references and lifetime are a concern on the right side. Non-copyability is a feature on the right side on the objects, but copyable and movable are inherent qualities of values. Okay, and we have polymorphism and composition. So this is the range of things that there can be between the reference semantic, which is the object-based things, and value semantics. I've taken this the screenshot from Juan Pedro Bolivar Puente. He speaks a lot about value types and immutable data structures, and he's given some very interesting talks about immutable, not only immutable, but about fitting value types in the real world applications. He also has a library. I will reference to it in my slide deck, which can help you with value-oriented programming. So as we see, operational specs, procedures on the left-hand side, shared mutable state, globals, object-oriented, shared pointer, mutex are the fact of reference semantics. Whereas on the right-hand side, pure functions, denotational specs, regular types, pass by value, const, functional programming, and const expert are the qualities. If you notice, there is a mutex there on the left-hand side at the bottom, but there is no mutex here. And no points for guessing, because you're dealing with values. When we say we have pure functions, we just are dealing with the parameters which have been passed to us. They are only with us, and they are our local objects. Given this condition, can you have a race condition with something else? Would you need to do mutual exclusion with something else? Absolutely no. So as far as you can stay in value land, your parallelism and concurrency is also pretty much sorted out. So very big benefit. Okay, so reference semantics are just highlighting the main concerns here. Have safety and efficiency concerns. They threat unsafety, like I just pointed out right now, is a possibility. Spooky action at a distance, making a change which you did not intend, or you calling a function which calling in the reference-based world. You calling something which calls something else, and finally you yourself again get called. Reentrancy is also a problem Dave Abrams actually adds to this list. And so incidental algorithms actually develop, as Sean Parent says. So the root of all suffering is attachment. References, holding on to each other, and really a lot of suffering you can get when you have these kind of problems, and your dream just collapses. This is any guesses from the movie Inception? Yes, not Deception. All right. I think we have a question here. Can I say value semantics is more of having concrete objects and variables and less or not? Yes. So you avoid pointers, which means pointer can refer to something very remote, and references, which is again referring to something remote, not with you in your current frame. And dynamic memory, yes, maybe, because you can even have pointers to somebody's local objects. It may not be dynamic. It may be 3 frames below you in a local object, but yeah, it will go out of scope. So it's not the lifetime issue which you will get from such kind of a thing, but you will get let's say concurrent modification, etc. Something like this. All right, I think we'll go next. So let's try to pass by value. Okay, and why not just pass the objects also by value? What's the big deal, right? Dave Abrams and others researched about this. They've written a paper. So many people with the name starting with D, except one, have written that paper. I'll just give you a glimpse. And they studied the mental models of the users using the reference semantics. Okay, and this is the paper. I will encourage you to go back and read, look it up and read implementation strategies for mutable value semantics. Okay, and it's not so they studied the mental models of even Python developers in at Google, and you know, this is an example which Dave just gave in May 2022, and it's highlighting what we actually mean when we pass by reference. Okay, so anybody wants to tell me what is a problem with passing by value, objects being passed by value? Okay, while you write up something. Copies being constructed. So yeah, I hear you. That's a very genuine problem. And this is something that they've also found out. So let's look at this quick example. I have not brought up my laser. I will. Okay, so here we see this is just a sort. I'll encourage you to go and see this talk. I might not do as much justice, but I'll definitely point out the outcome, the point made by Dave here. So this is a sort. It takes a vector by reference and a compare function. Okay, what can be wrong here? We have the standard library built just like this, and I think nothing is wrong there. But Dave points out that in your head, you assume that nothing else is changing this S while you have given this to the sort function. While sort is going on, if something changes, for example, he has strict it here. He's passing the less to sort here, and he's defined less as having a reference to V, because it looks like V is accessible from this lambda, and V is being modified in the comparison every time you touch it. And this is not what we ever had in mind. I'm sure he's playing a trick here, but this is exactly where you're not looking is where bugs will happen. Okay, and he's very right in pointing out that we do assume that this compare is not modifying the vector. Not only compare, anything else in the world is not modifying this vector while it is being sorted, right? It's an inherent assumption that we have in our head, but we hand it out a reference to something which is elsewhere, and other people also might have a reference to it, but we don't mean to actually do that. All we mean is what has been written here, that it there is a cost to copying the entire vector, and that's why you want to avoid it, and that's the reason why you're not passing by value. But actually you mean to, because you didn't expect anybody else to change it. So this was the point made by Dave in this presentation. It was a very enlightening issue raised. And we pass by reference only to avoid expensive copies. And I would also add that you pass by reference in order to avoid lookups in maps and hash maps and tables and trees. And the mental model still is actually pass by value. Okay, so really we don't mean to do it, but it's just that the language eagerly copies the entire vector. The object is copied, which we don't want, and or it is expensive basically, and that's forcing us to use reference, but actually we don't mean to use the same thing in two different places, really. Okay, so in line with Dave, I would like to see how we can sanitize with values. We have a couple of questions here. How are we doing on time? Okay. Does const reference have the problem of reference semantics? Yes, const reference has, because you got a const reference, but somebody else may have a read-write reference, and this is a typical issue with the race condition. You're only reading, but somebody else is modifying, so that will cause an issue. Mohan, but in real time, we tend to send the memory by making it const, and so the colleague can't write or tangle it. Well, not every time. The whole idea of programs is to change things, is to change data, is to change state, is to, I work in telecom software. You want to make the calls, your call should get into connecting stage, it should get into ringing, it should get into talking, it should get into disconnecting, or, handover if you're walking around and changing your cells. You actually mean to make these changes. If you don't allow any change, then your application or the whole program is no good. So there is change. There isn't only const in this world. So so for sure there is const. You can be very careful, and I agree with you. Maybe you will have very few of these problems if you stick to these good good habits and good styles of programming. But you would actually run into this problem somewhere, or somebody would run into the problem, and that is quite inadvertently, and this is why I'm pointing out this thing like Dave did. Okay, sanitizing with values. Let's see what we can do. We have all used sanitizers too much last 2-3 years. Okay, returning pointers. Let's say you have in your this is pointer based in your implementation create car. The reason you have this function to create car and returns a pointer is because it might be maybe an expensive operation. You have to go through a few steps, and so you want to make it once and hold on to it. Hold on to it in one place. But if you get back a pointer, there are several problems with it. Can you expect a null pointer back? Can you hold on to it, or is it just so? I've given you the name of this function, but if the name was not that clear and a little obscure, like find employee. If you have something like this and you got an employee pointer, how long can you hold on to it? Can you just keep a copy? Is one element returned, or are these several? Is that an array which decayed into a pointer, or it's just one object? Am I responsible for dealing with it? Do I delete? And again, the question comes, do I do simple delete or an array delete? Ownership, do I own this? Of course. So, I can consider it as my object, or am I sharing this? It's all of this is not just obvious with this. And just a trivia question. If you got a const pointer back, can it be deleted? I'll give you the answer. It's yes, because const objects also have a lifetime. It will go out of scope sometime, and for dynamically allocated ones, if it is dynamically allocated, because you cannot make that out also here, like you're getting a static memory or dynamic. But yeah, this is just for fun. Okay, so you decide to take the reins in your hands. You create oh, sorry, that should not be a pointer. It's an object of my car. And then you pass your object to create car. And this time the return is void, so no problems. All well. This is your in-out parameter. Of course, I would say no. Now create car is unsure of the pointer that it got inside the function create car. Should it check, can it be null? Is it supposed to delete what you got and then create a new one? Now the problem has been shifted to inside create car. You got a pointer. I know you'll be disciplined, but nothing in the contract of the function says and makes it clear. And I have seen gratuitous null pointer checks in the code base, and I'm so pained by it. Of course, there is no point of it. So why would somebody pass you the only object that you want to initialize and pass a null there? Maybe it's a way to say you please dynamically allocate. So in which case you have bigger problems. But if even if card reference was used, I'm sending a pointer here, but had you used a reference, even then we have another problem here. The construction happened on line 1, whereas initialization, its true values are got inside line 2. And this split is leaving room for something to happen in the middle. And this is not a happy thing. Over time, like I said, the spiral will go one way or the other, and maybe some code will creep inside between these two lines. And the association will separate, and somebody might end up using the mycar. Okay. Hopefully you write very small functions to be able to spot such things. Please do, if you don't already, make them really very small. Okay. So why not use unique pointer? Of course, it tells you that you are now the owner of this object. And of course, complying with the standard library, I call it make car now, not create car. So make car gives you a unique pointer. Ownership is clear. Complete object construction is done inside the function. And so it manages memory, and scope-based deallocation will happen. Automatic, everything is automatic, and no special handling is needed, because now you don't have a pointer in your assignment, move, destructor. You don't have to manually handle the pointer. This object will just do it. You can just assign to it. And this is very much, I think, a sum type is how they call it. So it's a sum type. It holds some value, and it's the value of a pointer, and it manages it fully. All right. Now you could use a shared pointer also if that's your game. But again, shared pointer, like we pointed, brings in sharing, and that is usually discouraged. Try not to. All right, so let's return an object. Oh, my animation was eager. So I wanted to ask you whether that first line would actually result in a car being constructed inside the function, and then an assignment or a copy construction happening in your object in which you take the car, but the return object is guaranteed to be elided in C++ 17. Compilers were able to do before that also, but this is a guarantee. So now you can directly say my car, just initialize it, just like you would initialize my int. Great. At least construction wise, we got equivalent. Okay, and not only this, I would like to point out that if car is a member of your of your class, just like an int could be a member of your class. Let's say int is age, and car. Let's say int is age of the car, and then there is a car. So both these things can initialize just like the lines we have written here in the body of your class. And those initializations will be used if you don't initialize these members of your class inside your constructors. Okay, so it's just like an int right now. Okay, and ignore the animation. Okay, passing pointers. Now, let's discuss about passing pointers. Similar problem as returning pointers. Now, like we discussed, the create car was not sure whether it got a null pointer or it is supposed to deallocate before using it, or can use it, whatever. So you know the problems we just discussed. So, I've seen code base full of these checks, and at least starting 2 indents inside because of the null check. And so, that's out of fear, because they know their code will not do it, but what if? And so rather than correcting the code, we are in this land of null pointer checks. Actually, null pointer is a mistake in programming. I think we are on our way to eliminating it. Hopefully that'll take a good long time, but hopefully we'll get there. Now, if you pass pointers, it's very well encouraged. And pointers and references, I'm treating both the same, because somebody gets your object, and this is okay as far as you are temporarily dealing with it. You are just handling it inside the function you have been passed. You're not saving its location somewhere else. etc. So if you don't do any wild things like that, passing pointers is actually okay and encouraged. There are some CPP core guidelines also which tell you about dealing with pointers, and please take a look at them. It's not the scope of this talk, but please know these well. Okay. So now let's talk about, so we talked about parameters in and out of functions. Now let's talk about inside the functions. Now here we have the issue of a copy being made, right? If you have a function called as fixed puncture on the tire, you give to it a value, the tire, and you get back another value, which is the tire, after it is fixed or something. And of course, you have a copy. Where's the copy? In the return? Hopefully not. You got that in C++17, that it's going to elide that copy. But this is a copy while passing it into the function. Okay. So what do? We make sure that we are able to pass an R value to it. Any temporary object or std moved object can be now passed to this, and you just have the cost of a move here. So make your value types movable. Of course, we have touched upon that, right? But is R value reference a reference? No, it's not actually. Okay, so you have your object now T in the local frame, and somebody else's object has been moved out into yours when they called your function. Okay, so that's totally safe. They just gave up, and you just got control. You just got all the data. And if your object is having 3, 4, let's say if this is a vector, or this is as big as a vector in its internal members, so you would have 32 bytes of copy happening. Much of this might even happen within the registers of the CPU, and you might end up not incurring any cost. If there is any observable difference in your constructor, in your move constructor, then I guess you will have to incur the cost of a move constructor, but that's a very small cost. I hope you're not making God objects with 25 fields. Okay, but that's beyond the scope of this talk. I hope you don't make big objects, otherwise you incur that much cost. It's not a problem with the methodology. It's a problem with the big object that has been created. Okay. All right. So this is now from Tony Van Erd, and it's a C++ cone. He loves to do these, and I like this one. Like, let's go through it. So a cone is a short story, just this much, and he usually fits them in 128 characters of a tweet, or maybe 2, but not more. 140 characters, right? Sorry, I'm too much 2 to the power. So a master comes to his disciple's place, and the disciple is honored. Master, I'm honored with your visit. And master says, I was walking out my dog. Your function, why does it take big common struct instead of just x and y? Okay. Why does it take big common struct instead of just x and y? Big common struct is where we keep x and y, master, the disciple says. Okay, just at the moment the dog barks, and the master says the dog is hungry. And being overwhelmed that the master has paid the disciple a visit at his place, he offers to prepare food for him or to feed him in whatever way he wanted to help. Very genuinely wanted to just help. And to this, the master said, no, just open the fridge and let him take what he wants. That's where x and y are, right? The food is. Okay, so thank you to Tony for this. I see the grand applause. I wish I could pass it to him. So the learning here is, you should not keep passing big common struct around. For example, the real situation, you have a a flat tire, a puncture in your tire, would you give your car for repair or just the tire? Right? Of course, you're smart people, C++ developers. Okay, so you fix the puncture by giving a car. This is so sad because inside you just have one line touching C, the car, and nothing else needing a long function, not needing the car in any way. Then why is this passed? Okay, why don't you pass the real object that is needed? You know what happens in time? In time, let's say I'll also, while I'm fixing this puncture, I'll also inflate the other tires and inflate all of the tires to a required level. And so you do a for each on the car just because you have an access here. Humans would take the easiest path. Anything good, electricity also does, water does. So do humans. They take the easiest path. They see this is a place where you have the car. And let me just write this range for and update all the, inflate all the tires. That's not the place. It's the place to fix a function. And when you mix up these kind of things, just because you pass the big common strut, the car, to this function, you're able to do much more than what you should be able to. And this is where the spiral, what I showed to you initially, the spiral pulls you down, okay, into mess. This is what Björn Strostrup was telling us when he said it should not tempt you to make the wrong kind of changes. So you should have it in you to stop yourself from doing this, think about what would be the right way to do it, and go and write that functionality. If you need function f, go write f if f is not already present. That's your job, and that's the right way to deal and maintain code. Okay, but here in terms of dealing with things, just deal with the values that you really are going to use. Okay, not the whole fridge, right? Single responsibility, we talked about, solid was mentioned in the initial list of desirable features, and single responsibility is one of them. Okay, and again, this hits us on other counts also. For example, this cannot be the substitutability of other types in this won't be there. Some of the other rules talk about it. I'll not get classical here. Okay, I'll go next. So this is what causes the title is creepy, because this is a scope creep coming in the function and then doing things which it should not. And you don't have an explanation of why something happened. So the law of Demeter tells us that you actually provide just the thing that you have to work on and no more. So it's a principle of least knowledge. Just provide the thing that the function has to work on. And we have seen this in mythology. You know much better. Poor Hanuman did not know how what Sanjeevani Booty looks like. So he got the whole thing, did the right thing at his time. But do you not know what this fixed puncture is going to work on and pass the right kind of object only? You are aware. Don't pass the entire car, pass just the tire, okay? And make functions which take just that, because you're also the author of such functions. So returning bool, we have seen this fixed puncture returns a bool. And, you know, the caller is now, because of the bool being returned, is now forced to check in every place that it is invoking fixed puncture. And maybe it could fail, maybe it would fail, but this leads to unmaintainability and also, you know, nested code to a lot of levels. And I think that's what I'm saying. Baba zero gravity, I can float on water, as you see, and zero cost proponent. What does this Baba say? It says that bool returns are the root cause of unmaintainability. Okay, this is one of the root causes. And as you see here, this is the whole reasoning. Bool returns make you check conditions. Conditions introduce nesting in your code. Nesting gives you combinations. Often, if there are n conditions, 2 raised to n, might be less. The combinations of the various possibilities give you untestable code, because if there are 64 parts through your function, I'm sure you're not going to test most of them. Okay, many of them, I think, okay, being nice people, we'll do it. We'll try to do it, but it won't be 100%, right? And the untestability gives you really unmaintainability. Now you're not really sure what's happening in this function. We have all seen those 200-line functions. And if you're the author of some such functions, stop. This is the time to realize that you need to break into functions. Okay, if you see a function saying, step 1, first, validate the input. Second, next, parse the thing. Third, look up the something. And then fourth, process the message. Fifth, send it to the intended recipient. Okay, suppose this is something that you're doing in this big function. As you can see, these places where you have annotated, these are the right places where you can just create the functions. I hope you know what she's saying about Baba zero gravity, zero cost proponent. आप मान गए और बोलूं? So once more for you, return of bools are the root cause of unmaintainability. Okay. Okay, return the new value instead. Yes. Why don't you return the new tire? So fix the puncture and give back a tire. So because everything is a value, because tire can be represented by a few values, the rim size, the thickness, the pressure maybe inside it, and that's it. A few of these values, and I'm sure I'm not doing a good job, but I guess you know what I'm saying. A few things, and you return it. It's fine. And many of these operations give you at most will be elided, and at most they would give you hopefully not a copy. If tire is not movable, then you incur the cost of a copy. Okay. Okay, so avoid bool returns. So how to avoid? Maybe you can throw an exception. Okay, so you throw a runtime exception that you're not able to handle a condition X, Y, Z, and the caller will do it. And hook or by crook, they will have to handle this, because this is unavoidable. You have to catch exceptions. It's a foolproof way of making sure the caller has done something about it. But it is also the reason for some crashes if the caller has not handled it. Plus, it gives you some. It's not very efficient to have exceptions. But again, to worry prematurely about exceptions being your big worry, just please measure, okay, before you pick a strategy. But have a strategy. If your strategy is to do exceptions, you do that. Okay. Maybe you could use optional T. Now, this was introduced in C++ 17. Optional T is a sum type. Okay, sum type is something that can hold something else, and this can optionally hold a T. Okay, so if you are fixing a puncture, and maybe there is a possibility you are not able to do it, maybe that's a reality, you give back not a T but an option of T. And so the caller again is they are forced to call a dot value or dereference with a star operator to get the value. Okay, and they are forced to check it. And so this cannot go wrong because they cannot use it like a tire. Okay, for sure. So optional forces you. This is a very good and foolproof way of having things in your code which are for sure certain. And this is also a way. So go ahead and please return an optional if you're not sure that always an object will be returned. Okay, I'll just check the question. How about returning enums? They appear to be the same then. Enums are very low cost. They are like an integer or a number, and they can be returned. But if you mean to say that an optional, that you won't always have the enum. For example, we do have this kind of a condition that we have an environment variable which says what is your log level, a very common condition everywhere you might have. So you have, you will either expect a word debug, a warning, an error, or something like this. Okay, few of these. If the provided text is India, then you cannot parse out an enum. And in that case, you might want to communicate that this enum is an optional enum. I'm not sure whether I'll be always able to provide this to you. So go ahead and do it. You see, the pointers have a problem. Pointers also can hold null pointer, and the zero value means that there is no object, but you are not sure ever whether the source that they went to actually had a null object, or you actually the operation failed and so you have a null pointer return. Okay, and so setting aside a value, for example, string has set aside a value of /0 to signify the end. So they have sacrificed the possibility that the string can itself have a /0 in it. Now with Unicode and all, I don't think it's a possibility still, but hey, who cares? Why are you putting this restriction and decreasing the domain of that value? The value can hold 256 numbers, but not in the case of a strings character. It can only hold 255 because 0 is reserved as a special meaning, null character. Okay, and I see strings being used in an Apache library called as thrift, which is for communication between machines, and a protocol-based one that uses strings to exchange byte buffers, and it works. Everything works fine, but if you call a C string on it, you will not see the right thing. All right, so we can do this, and when you get back an optional, you assign it back to the tire where you took it out from. Okay, now you might think that this is a copy of the value which is happening, so of course there is help for that. The optional that you get is going to be copied if you do this. Okay, because this is an L value here, and if you call the value of L value, you will get the reference, but it will be the reference of that object. It won't be a moved out one. So you have to actually explicitly move it out of the enum. But if you do this, you have actually moved out a read write reference that you had from the fix.value. So fix.value gives you a tref, but you have moved out from that tref because you have read write access to it. It's not a const. But the right way to do it is to actually move the optional itself and then take the value. So there is an overload for this function which gives you the R value at all times. So that assignment becomes and stays as R value. Okay, maybe just a fine point I thought I'll just cover. But of course, if you do optional, you have very ugly ifs because everything can fail. You have a set of operations that you have to do. Everything can fail. But now in C++23, a monadic interface has been added to std optional. So let's consider that you have two more functions called as wash and polish for the tires. They take a tire, they give back a tire. Okay, and you want to do this. You fix the puncture of your left back wheel of your left back tire, and then you inflate it to 32 psi, transform it into a washed tire, and then polish it. And if finally you don't have anything inside the optional, it's empty. In case it is empty, you want an empty tire to be returned from here. So these are the functions that I've listed here. They are called as the monadic interface. They try to work with the value inside the wrapper of std optional. Okay, and it's a very interesting way. This is how Rust code is written pretty normally, and we are also able to do that now with the monadic interface on std optional. Okay, similar to this, std expected has come, which can not only hold optionally a t, but the other option of it is an error. The e there is an error type, and so you don't really get the signal that something bad happened, something wrong happened, but you also get the intimation about what really happened and what went wrong inside the operation. What is the error really? Okay, and the implementation and the interface looks pretty much like std optional. I leave that for you as an exercise, but please, this is the better way of implementing error handling. So as you see, you are just applying a series of functions to something, and everything is passing by value, and most of the time it is just temporaries, which all of which can be elided, and you finally pay very less cost on maybe one or two moves. at the end of all those operations. Okay. So object to values. So now we have looked at functions, how to pass and return from them, how to write inside it. Can we look at the structural aspects, which is the class and the struct? So let's look at this class car. It is it has an owner pointer. So left hand side is the object world. Okay. It has an owner pointer. It has 4 tires, left, right, front and back. Okay. And it has an engine. It has many of these operations. So if I were to show you this class completely fully built, it would span 2-3 pages, I guess. And this is the car that you might have in an object-oriented system. As you see, there is a reference to the owner of the car. There are tires, because the tires can change anytime. So the user thought that it would be a good idea to have pointers. And the engine is an in-place member. Okay. Now in the value side, you would make this public if changing the internals is okay with you. If there's an invariance to guard, then please keep these things as private, and then you'll have to provide things. But if you don't care, for example, owner ID is held here and not the owner pointer. You can anytime look up the owner only when you want, and you don't have to hold on to the owner and cause lifetime issues. So you have the ID, which can be looked up. You have 4 tires in place, and you have the engine just like before. And we don't write any other code if this is a struct the way it has been defined, public one. Everything is done by the compiler. This is the rule of 0, and we love it. And so let's look at another very real life example from the telecommunication world about the call that changed the destiny. This is the song from Backstreet Boys. I don't know if you have heard. So let's look at a call class. Okay, so you're working in a system which makes calls. I had previously told you about that. Calls are in various stages, and we are, let's say, in a telecommunication system managing calls. Okay, so we have a call class as expected, and we have a number of members here inside it, and they already look too many. I'll just uncomment a little step by step. So if you see, this is mentioned against the 2 members up there, unconnected. So these 2 members are in play when the call is actually in unconnected state. Okay, when the call is active, you actually have a socket, live socket to the remote. When you are transmitting, actually speaking, you have an audio codec. This is how your voice is encoded, and a timer to keep alive, like I'm there. Okay. And you have an on-hold possibility. Somebody kept you on hold, or you have kept somebody on hold. So you stream music to them. Okay. And this is the call. Okay. We have just talked about the few stages that states that the call can have, and how many of these members that we have had to keep. But as you know, all of these members are there at all times. This is a product type, the way it is defined in functional language. All of these things are possible at the same time. And so, you have access to reconnection timer even when you are in hold. You have access to music stream when you are in transmitting. And this is a way of things going wrong. I think we have some of these state-based issues here, but we have a better way of doing things. Let's define every state as a struct. So let's say we have a state unconnected with the 2 fields that were related to it. The active TX with the 3 fields that are related to that one. Active on hold with just the 2 things that are related to active on hold. And so with that, your call can now be represented in something called as std variant, which I'm sure you might know from C++17. It can hold many of an object. It can hold one and only one object of one of many types. Okay, one object of many types. And so in its declaration, you would say what kind of objects you would hold. In our case, we have these 3 objects of unconnected, active transmit, and active on hold. types, and I've tried to keep it simple, but there could be a few. But so if you know these are the only possibilities in your system, STD variant is a good way of doing it. Okay, it has some cool optimizations also, and a very bad interface to use it also. There are pluses and minuses, but you got the right tools to be efficient with only one of these possibilities. So now, since you have only one of, this is like a union which never forgets what kind of type it has right now. Okay, it'll always know. With that, all of those fields which are just about the state and state dependent fields have all gone away. And this using call state is what we are using here as the state of the call. And this is the only thing which, just talking about the state management of the call here, this is the only thing which is there in the call, and it becomes so simple. And I'll also remind and point out to you that this is a value type. It has one of these three values and only one of these three values, okay, at a time. So the state machine that you would write based on this, for example, now a disconnect comes. What happens if you get a disconnect when you're in active transmit, when you're in active hold, or when you are not even connected? What does it mean? So you can actually manage the state of these by handling the corresponding events to these states in these in a simple function. And so this overload of the handle function takes all the three kinds of states that we have defined in our system and an event and mashes them up and generates a new call state, which will be your new state of the call. Okay, and how do you do it? This is the STD visit. We are not getting into syntax here, but STD visit takes two things. First is a lambda which can work on the possible value inside each of the possible values inside the variant and the variant itself. Okay, in this case we are passing a third thing, which is the event also. So obviously both of those will be passed to the lambdas, and this is a trick. Basically this is not in the standard, but overload is a trick. There's a very small construct that you have to use to get this. So you add three lambdas inside, and all those three lambdas are available as the call operator of this object overload that you're passing to it. So the overload becomes the lambda with three possibilities, and you call the visit to it. Visit can unpack the state and call the right function with the right type. And so based on the type, you are very sure that only the right thing can happen. If you introduce a fourth state into the system, and this function is not actually handling that state, you will get a hard compilation error, and you cannot have an application which will do something wrong. So there you go. You have this way of managing using some types, the STD variant, all the possible states in your call. Okay, so if we just take a look at a real life application in telecom, we have a caller, callee, the call itself, and transactions. These are some of the things which I know by knowledge are supposed to be looked up first thing when something comes, a message comes or something. But there are many transitive things which don't have to be reference or heavy objects, including things like connections, sockets, and message buffer. They're just trivial objects which can be passed around if you manage and if you use RAI kind of things. So many of these, much of your vocabulary, most of the application becomes value-based and functional, and only for some of these things, which are the real state that you want to modify and manage in the application, you have something like this as object kind of things. And just a last recommendation on flow: have a unidirectional flow. If you pass something to a function, you just have passed to it. You don't have it anymore. This is the way values work. And if you have only local objects, of course, there is no thread contention, no race condition, no concurrent issues that we discussed. Async, no problem. Local objects cannot have contention, right? So, okay, I'm going to skip some of these. I think I had, yeah. So how can we afford to have these many copies? Some copies are elided by the standard. Compiler can deduce some and eliminate some. Most should just end up being the cost of a move. But if For everything rest else, you have to pay for the copies. Okay. If your application, if your objects are not movable, then you have to do that. Okay. So we go on. Not everything is performance critical. Please measure before you optimize and make it difficult for the human to edit and modify. I have done things like optimizing parts which really don't count, and I don't see a difference in life. Don't do that. Measure, and only if it is pointed out by performance measurements, something is a problem, only then you change that part to maybe have eliminate copies or references. Okay. So for the second time at this conference, I bring to you Donald Knuth. Premature optimization is the root of all evils. We were told by Mike yesterday. 97% of the times this is the case. For the 3%, you go for what Mike told you. All right. So values. Make everything a value as far as possible. Optimize only the parts that you must and build it for the reader and the maintainer. Thank you very much.